Okay, so this unit, gas laws, is going to be a pretty big shift from what we've just been doing. It's going to kind of be a relief. I think you guys are going to like this unit because there's more math involved. It's a lot of math. Very little conceptual stuff, which is what all last unit was, a bunch of writing formulas and things. So I think you're going to like this unit better. Students traditionally score higher, so when these next test grades come out and you didn't like your Unit 2 score, don't worry, you have a chance to make it up on this Unit 3 exam. So the basis of gases, when we talk about gases, we're often doing gas calculations. And we do gas calculations. There's some qualities of gas that we need to be able to talk about. We need to understand the concept of pressure. We need to be able to understand the concept of temperature. And then we often are dealing with gas volumes. All right? So there is a standard temperature and pressure in the whole world of gas laws. It's different than the standard temperature and pressure in everything else. Thermochemistry, equilibrium, acid-base chemistry, electrochemistry, all of those have a different standard temperature. But they all have the same standard pressure. Does anyone remember what units of pressure we deal with? 1 atm is standard pressure. 760 torr, good, which is equivalent to, there's one more. Exactly, 760 millimeters of mercury. When you get to physics gas laws, which you're going to hit, I think, like right in the, I feel like they hit it either right before Christmas or right when you come back in January. You guys are going to be doing PV equals nRT, perv-nert, and all these kinds of things. They call it piv-nert, I call it perv-nert. But you're going to be doing everything instead of an ATM in kilopascals. Does anyone know that transition number? Yeah, I think it's like 101.325 kilopascals is standard pressure. We're not going to use it very often. I would know it because I don't know if on the AP they're going to throw a conversion for that on there or give something to you in kilopascals. I don't want you to freak out. I want you to be able to use it. It's no big whoop. But here they have, this is the old-timey barometer. This barometer measures in millimeters of mercury, literally. It's literally how many millimeters of mercury in a column is created when you invert a UDometer like this, and the atmosphere pushes down on it, which leads to a certain height of this column. At standard pressure, the height of this column is 760 millimeters of mercury. Does anyone know why we would use mercury in one of these instead of water? Potentially. Not the primary reason. Water evaporates is what was said. Could be a reason, but not primary. Any other ideas why we wouldn't use water? What else can you tell me about mercury? It wouldn't affect it that much. What were you going to say? You forgot? Okay. Yes, Amelia? It's easier to see? No. Has anyone, it's not encouraged that you play with mercury, but has anyone touched mercury ever? Has anyone picked it up? It's not super temperature dependent. You're thinking about a mercury thermometer? Yeah. It is nonpolar, so it is more affected by temperature than water would be, but that's not why we couldn't use it. Well, let me tell you a story, and then maybe you can answer my question. So Miss Sage and I one year attempted to, out of my window, make a water barometer. It's possible. But we took a tube, and we had a bucket down on the ground floor, and we fed the tube all the way to the ground. And then we had to get the water up the tube to even start it in order to get it equilibrated. Why are we dropping it all the way down like that? Why can't we do it right here? Mercury is incredibly dense. Okay? So when the atmosphere pushes on it, we get very small changes in millimeters worth of changes. And thus, in order for us to construct a water barometer, it has to be like 3 stories high. So it's not a real efficient use of space. It would be hard to transport that around. Okay, on the wall back there, you see the thermometer clock-looking thing? That's a thermometer. Underneath it is a barometer, and in it is mercury. So the mercury, being as dense as it is, allows us to do a more appropriate scaled measurement of changes. Make sense? Okay. All right, so I need you to know the conversions between all these. For standard temperature, what's standard temperature in the world of gases? Not 25. 25 is in the world of everything else. 0 degrees Celsius, or what's 273? Kelvin. Kelvin's going to be required in this unit. Any calculation you do has to be in Kelvin. You never, ever, 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 ever plug in a degree Celsius into an equation and solve. You never use a combined gas law with a degree Celsius. You never do dimensional analysis with a degree Celsius. It always has to be in Kelvin. Does anyone know why we went ahead and, or why it was developed that way? Why was Kelvin, the Kelvin scale, used? No. 0 Kelvin is as low as we get. What does that keep us from dealing with? Negative numbers. If we were in Celsius, we'd be getting negative numbers, and if you think about a number line, we'd be worried about volumes, like what our volumes then. I don't know, it would just totally mess things up. So we are going to stay in the positive world of Kelvin in this unit. And moving on, there are some gas laws that you might remember. Peas and vegetables on the table equals peas and vegetables on the table. This is something called the combined gas law. This is on the AP sheet. I don't like doing formulas. I prefer you to do dimensional analysis because it makes you think. But if you're more comfortable with the formulas, you can use the combined gas law. And when you're doing the combined gas law, you just get rid of anything in the equation that's constant. So in this problem up here, which I'll show you, we're only looking at changes in pressure and volume. We're not looking at temperature change, so we would just cross this out, and this would be the equation we'd use. So you can manipulate the combined gas law to solve any of these problems. I'm not going to. If you want me to go over that with you, you can come in separate and I'll show you, but I prefer you to do dimensional analysis, which is what we're about to do. Okay? So, Boyle's law. Boyle's law is the relationship between pressure and volume. You don't have to memorize that, but I do have a story, because stories are good. So I'm going to pick on Matthew just because I looked at you. He was going to prom, and he was getting ready for prom, and he looked in the mirror, and he had a boil on his face. He was peeved that he had a boil on his face. All right? So Boyle's law, pressure, and volume. So I was taking CPR about 6 years ago. I can't remember when it was. It was a long time ago. It was longer than that. And we were doing compressions. And this guy was trying to be Mr. Smarty Pants. So it's like, and when you compress and changes the pressure, the volume of the lungs change, and that's Charles's law. And I was like, no, it's not. It's not. It's Boyle's law. And we kind of argued, and he was wrong. But anyway, so it came in handy. It might help you one day, like it helped me make someone look stupid. It was awesome. Just kidding. So Boyle's law is pressure volume. What is that relationship? If I have a certain volume and I add pressure to it, what happens to the volume? D goes down. And then if I have like a Nerf ball, and if I release the pressure, the volume increases. So what is that, direct or indirect relationship? Indirect relationship. So when you're starting these problems, I highly suggest you just kind of jot down your numbers before and after, and you're going to see it's really easy to set up in dimensional analysis. So this says, a sample of SF6 occupies a container of variable volume. So it could be a balloon, something like that. If the sample originally occupies the volume of 50.0 mils at 755 millimeters of mercury, calculate the pressure at which must be exerted to lower the volume to 25.0 mils. So this is like a before and after scenario. When it's a before and after thing, you can use the combined gas law or do this dimensional analysis. So I always say, start with what you're looking for. What are we looking for? Pressure. So we're going to start with pressure. And we're going to multiply this pressure by the ratio of volumes that make it come out bigger or smaller, whichever way we want it. So looking here, we're going down in volume to get down in volume, do we increase or decrease the pressure? Down in volume. Wait. Yeah, increase. I got to listen to my own head, not listen to the voices around me. So as volume decreases, pressure had to increase. So we're going to multiply by a ratio of those two volumes to make pressure go up. Is that going to be 50 over 25 or 25 over 50? 50 over, does everyone get that? And does it matter what these units are in? No, because look, as long as they're in the same unit, they have to be in the same unit, but we're not required to put that in liters. All right, so looks to me like we're dealing in a 3 sig fig world here. 1,510, and what is our unit? Millimeters. And did pressure go up? Yes, it did. If you just plug this into a PV equals PV equation, where you put in PV, you put in V and P, and then you put in V and solve for P, which you could do, I just don't like it because you're not thinking. You're just plugging and chugging and saying things like, oh, sugar's insoluble. That's kind of the same thing. I want you to think about what you're doing. Okay. Are we good? Next one. This is Avogadros Law. Avogadros Law is a relationship between moles. Avogadros Law, I don't have a funny story for it. It just makes sense. It's a relationship between moles and volume. So if you have a certain number of moles of something, you're going to have more or less. Okay, if you have more moles of a gas, you're going to have bigger or smaller volume. Bigger volume. And that's literally all it is. There's a direct relationship between those. I'm going to turn this off because it's annoying me, and I don't know who's trying to call me this many times. Dink. Okay. All right, so let's do this. We are looking for volume and moles. Suppose we have 12.2 liters of a sample containing 0.5 moles of oxygen. And it gives you a 1 atm and 25 degrees. Notice they don't ask you anything about the pressure or temperature anymore, so I'm not even going to write those down. Those are going to remain constant. If all of the oxygen were converted to ozone, what would be the volume of the ozone? So what we need to know is the moles of the ozone. Because I don't care what the gas is. X number of moles of gas at the same temperature and pressure, regardless of what the gas is, take up the same amount of volume. If I have neon, if I have methane, if I have the same number of moles, they take up the same volume. So if we're starting with 0.5 moles of the O2, how do I get to moles of the O3? 3 to 2. 3 on the bottom, 2 on the top will give me moles of O3. Someone tell me what that is. 2/3 of that. 0.5 times 2/3. 0.3 repeating? Yes? Yes. 0.33. I'll do 2 sig figs. 0.33. Okay. So now we can do the problem. Start with what we're looking for. 12.2 liters. All right. And then we have, what are we doing? We are going down in moles, so what's going to happen to the volume? It's going to go down, so what ratio I'm going to multiply by? Yep. And it doesn't matter moles of what. Again, whatever mole, that's the thing that's cool about gases. It doesn't matter what you have. If you're at the same temperature and pressure, your volume is going to be the same. All right. And what do we get? So 8.1. 8.1, what's the unit? Liters. 8.1 liters. Okay? Another way you could have done this, I don't know if any of you thought about this, and it's kind of a trick, but I didn't want to do it because I wanted you to understand it's really a relationship between moles and volume. You could have just put the mole ratio, 3 to 2 or 2 to 3, straight up in here, because that's what's changing it. Y'all see that? So I could have said 12.2 liters. I'm noticing I'm making less moles of gas. So that's going to make the volume smaller because I have less moles of gas on the right side, so the volume will be smaller, so I multiply by 2/3. And that would have given me the exact same answer. So whichever way you want to do it is cool. Don't care. All right. Now we have two different gas laws that include temperature. There's Charles' Law and Gay-Lussac's Law. Charles' Law talks about temperature and volume. So Charlie Brown, Charlie's Angels, Charles in Charge. Have y'all seen any of these shows? You haven't seen Charles in Charge with Scott Baio? Oh my gosh, I'm so old. And then Charlie's Angels you've heard of, right? It used to be a TV show prior to ever having seen the movies. All of those things are on TV. So if there's another Charles on TV that you know of, you can use that in your head. And again, it's really Gay-Lussac's Law, but Americans say Gay-Lussac's Law, which leads to the word gay. So I have a story. What two girls can I pick on? Who likes to shop? I have a feeling I'm going to pick on you two. I'm going to pick on Abby and Alex. Abby and Alex are at the mall, okay? They're hanging out Forever 21, and then they walk outside, and Abby's like, oh my God, that guy over there, he's so cute. And Alex is like, Abby, he's gay. And Abby's like, oh, what a pity. PT. Pressure temperature. It's a pity he's gay. Not because being gay is wrong or anything. I'm just saying she's a girl and she likes boys, and, you know, he might not like her because he's gay. And that's a pity. All right. So here's the conversion. You need to be able to go back and forth between Kelvin and Celsius without thinking. Just do it, natural. Wait, I'm not going to tell you not to think. Let me take that back. With a lot of thinking, you need to be able to go back and forth between Celsius and Kelvin. All right, this is the use of the combined gas law. We're going to have potentially multiple things changing here. We're going to have two conditions changing in number 4. Number 3, though, we're just going to see the difference with volume and temperature, which is what law? Temperature and volume? Charles's law. Temperature, volume, TV. All right, so we have 545 mils of a sample of nitrogen gas, initially at negative 220 degrees Celsius. It's heated to 100 degrees Celsius. Oh, I meant to put that down here, whatever. Calculate the new volume. All right, so we're going from here to here. What's the first thing you see that's wrong? Celsius. So we got to get both of these in Kelvin. This I can do in my head, 373 Kelvin. What's this one? 53 Kelvin. Okay. All right. So to 2 sig figs, oh, this is really 1. I'm going to make that 3. We'll say it's 2 sig figs. To 2 sig figs, what is my new volume? Start with what we're looking for. We're looking for volume. Temperature is going what? Up. If temperature goes up, what naturally happens to volume of gases? Goes up. So my ratio will be 373 over 53. So to 2 sig figs, what is my answer? Say it again. 3,800 mils. Does that everyone agree with 3,800? Okay, we'll stick with 3,800. All right, looking at this next one. This is a combined gas law problem that if you were to use it, you'd use all 3 variables. Don't let it freak you out. It's not hard at all. It's not hard at all. It's just you're going to take one variable at a time. So calculate the volume of helium, so looking for volume, at negative 33 degrees Celsius and 1.23 atm. If it occupies a volume of 2.34 liters at 54.5 degrees Celsius and 1026 millimeters of mercury. I like writing it out because it makes me see I'm actually going this direction here. I'm taking these known, and I want to figure out what this is going to be at these conditions. Okay, it keeps my conditions together by jotting it down. It makes the work easier. So I'm going to volume. I'm going to start with volume, but I can't put some stuff in. I got some issues. What's one of my issues? Got to get my temperatures in Kelvin. So what is negative 33 in Kelvin? 240 K. And what is my temperature in Celsius over here, in Kelvin over here? 327.5 K. All right, so I can get rid of those. I have another problem. What's wrong with my pressure? They need to be same. Do you have to convert to one or the other? No, you don't. You can do either. I tend to always just divide by 760 to get me 2 atmospheres. That's just a habit I have if I have to convert. And considering when you get to universal gas constant in PV equals nRT, and it has an atmosphere unit in it, you have to be in atmospheres for that. So get into the habit of converting to atmospheres. So 102.6 divided by 760 gives you what? 1.35 atmospheres, which matches up nicely there. All right, so start with what I'm looking for. I'm looking for volume, so I'm going to start with volume. So you don't try to do a whole bunch of stuff at once. Pick one of the variables and apply it individually how it affects the volume. So let's start with temperature. From here to here, from 327 to 240, that's going down. What's happening to volume if temperature goes down? It goes down. When you go outside in the wintertime, the basketball is outside, or your whatever, your tires, all that stuff's all flat, right? Because the volume of the gas goes down. So we need to multiply by what ratio? 240 over 327.5, and that will make that go down. Now let's look at the pressure. We're going from 1.35 to 1.25. As pressure eases up, goes down, what happens to volume? It increases. If I have a Nerf ball and I release the pressure on it, it's going to get bigger, right? So I need to make 2.34 get bigger by multiplying by what ratio? Over 1.23. All right, so to 2 sig, are we at 2? No, we're at 3 sig figs. 3 sig figs, what is my final volume? .88 liters. Who won? Pressure or volume? They were making different, pressure or temperature. They were making different things happen. Yeah, temperature won, it looks like. All right, are we good? Okay, one last little thing. It's called Dalton's Law, and it's actually not a little thing. It's actually a pretty important thing. We did this in pre-AP. I don't know if you did this in regular. But what Dalton's Law basically says is that the total pressure of all the gases in this room, for instance, is equal to the partial pressures summed, added up. So the total pressure in here is equal to the pressure of oxygen, the pressure of nitrogen, the pressure of helium, if there's any, CO2, all of that stuff added. It's kind of a common sense kind of rule. Where this applies in what we're doing now is in our experimental life. Experimentally, for us to collect gases, we normally do them over water. So everyone has done this. In pre-AP, you guys used a burette or a eudiometer, and you put HCl on the bottom, and you filled it slowly with water, and then you took a little piece of magnesium and hung it in there, and then you inverted it and started a reaction, and you dunked it in water. And you waited for the reaction, all the hydrogen gas to get collected in that eudiometer. The fact you were collecting the hydrogen in that water means collected over water. Were any of y'all in level chemistry in here? Did everyone in here take pre-AP? No. So you guys did a lighter underwater with a graduated cylinder. Do you remember that? It was a butane lighter. Not really. Okay. So you guys did it as well, where you collect gas over water, because we can't collect we can't collect gas like out of the sky, right? If we're underwater, that's what we would look like if we tried to collect gas out of the sky. If we're underwater, we're collecting it in the form of a bubble, and that can be caught, right? And that's pure gas. But it's not 100% pure, because when you collect over water, in addition, so if you have your eudiometer that we had, our inverted burette thing, in here you had your gas, partial pressure of your gas. In the case of this one, it was hydrogen. But because you collected over water, you do have some water vapor in there. There is a little bit. So we have to subtract that off to get just the pressure of the gas alone. Okay? So how do you know to do that? When you see the words collected over water. If you see that on any problem, underline it and go, oh, I have to do that other step. It's not hard. You just subtract off the water vapor pressure. So here it says, experimentally, oxygen gas is frequently collected over water. Ugh. When a sample of oxygen gas produced from a chemical reaction is collected over water at 24 degrees Celsius, the total pressure was 765. So pressure total is going to be equal to the pressure of our oxygen plus the pressure of the water. Okay? Our total pressure, they told, was 765. If you get a problem and they say the atmospheric pressure, we make the atmospheric pressure equal to the total pressure in our experiments. So when they give you atmospheric pressure, that is the total pressure. Okay? We want the pressure of the oxygen. Any idea how to find the pressure, partial pressure of the water? There's a table. There sure is. Go look at the back of your notes. And look at 24 degrees Celsius and see if you can find. Did everyone find it? 22.4. What's the unit? Torr, which is great. That's good news because torr is equal to millimeter of mercury, right? So we don't have to do any converting. We can just subtract. So all we have to do is take, did y'all find 22.4? You're going to need to be able to look at a table and find it. If you're not provided with a table, the water vapor pressure will be given to you in the problem. All right, so what is our partial pressure of oxygen then? Since this is a subtraction, we're going to subtract and round to what? Lowest number of what? Decimals, which is 0 decimals. What is it? 743 millimeters. Do y'all agree? Okay, so that's what we need to do when we're doing our next problem. We're going to have to do this in order to even do the dimensional analysis. So it's just a really long pre-work in order to get this done. So our last problem. Here we go. 235 mil sample of gas. 235 mil was collected over water. Do something, underline it, circle it, something. At a temperature of 28 degrees Celsius and a low pressure day of 738 torr. Report what volume, we're looking for volume, would have at dry STP conditions. Tell me what that is. Temperature? Kelvin. And torr? 760. So they're saying dry. So that's another hint that, hey, I need to subtract off the water vapor pressure, which I will. But first, I want to fix this because it drives me crazy. So what is that really? 301K. Okay, so that's fixed. Now, what do we have to fix? Which one of these are collected? Which one is the collected side, the left or the right? Left. This is the collected pressure, right? We want to convert it to the dry pressure of this. So this is the wet pressure. We need to get rid of the water vapor pressure. So what they gave us is the total. That's equal to the pressure of my, I don't know what the gas is, I'm just going to call it G, plus whatever the water vapor pressure is at 28 degrees Celsius. So find that on your table. 28. .3. All right, don't round. Just go ahead and subtract. Don't round to sig figs. I never round to sig figs until the very last step. So let's just go ahead and subtract here. And what do we get for the pressure of the gas? What? 709.7 torr. All right, so that's the torr we're going to use instead. Okay? So now we just do our two-step dimensional analysis. Start with what we're looking for, 235 mils. We're going from here, here to here, right? Whoa. So this is our start, this is our finish. So temperature is going down. What happens to volume when temperature goes down? Volume decreases, so my ratio is over 301. All right, now we can look at pressure. Pressure is going up. If pressure goes up, what happens to volume? Goes down, so I multiply by over 760. Okay. So to 2 sig figs, what do we get? 2 sig figs because of our original temp. After the conversion, I know it's not anymore, but originally our precision was 2 sig figs, or accuracy, excuse me. What do we say, my friends? Oh, you know what? But we didn't use the 28, did we? Let's do 3. Yeah. 207. Yeah, everybody? 207 mils. And it should have gone down because it went down in both cases. Pressure and volume. Pressure and temperature made that volume go down. Can I get a second on that value? No one's saying anything. 190? 199. Y'all were too quiet. I knew something was wrong. 199 mils of gas. Okay, so here's the deal. This stuff seems really easy, right? But there's a lot of curveballs that you can get in unlimited numbers of problems that you can see. My job as a teacher is to expose you to the basics, and in order for you to be successful on the AP, you need to be able to handle curveballs when you're by yourself. So that's why you need to do your homework, because the homework, even though it covers these topics, will have some different versions of the problems that you need to be able to do. So you have to be doing your homework. These are super short and easy lectures. Doesn't mean the problems are always going to be super short and easy. All right? So do those problems, and if you have questions, come and ask me.